videos, so it's easier to keep track of them for you guys. All right, so starting off with a very, very important theorem in algebra. This is the fundamental theorem of algebra. Okay, it's got to be important if it's the fundamental theorem of algebra. It is. Okay, the theorem itself is actually not very useful. It says every polynomial function of degree n, where n is greater than or equal to 1, has at least one zero, whereas 0 may be a complex number. Well, big deal. Okay, that doesn't really help us very much. The corollary is extremely useful. And when I talk about the fundamental theorem of algebra, I'm always talking about the corollary. This is a big deal. Every polynomial function with a positive degree, which is the only kind you can have, right? Degree of the polynomial is greater than or equal to 1. Every polynomial that fits that criterion has exactly n zeros, including multiplicities. Okay, that's huge. That's so important. We'll make use of that today. Now, a really important part of that is this little fine print at the bottom, including multiplicities. Okay, so what does that mean? Let's look at an example. What if we have a polynomial in factored form? Okay, so say we have something like, f of x in factored form equals x minus 2 squared times 2x minus 3, how about times 4? Okay, so there's my polynomial in factored form. Well, when we want to find zeros, zeros are just the values we get, the values of x that make the function equal to 0, right? So if I want to find zeros, then I would just set my polynomial equal to 0 and solve. Okay, just like we did with quadratics. So what are the solutions then? If I apply the zero product property here, what do we get for our zeros? What are the values that x could have? Remember the zero product property, right? We know that the product of factors can only equal 0 when we're multiplying by 0, when individual factors are 0. So what's the 0 of our first factor? 2. Everybody agree? If I set it equal to 0 and solve, I get x equals 2. How about the second one? You can do that in your head. If I set that equal to 0 and solve, I'm just pushing the 3 over and dividing by 2, right? So what do I get? 3 halves? Okay. Well, hold on. That doesn't seem to follow fundamental theorem of algebra. What's the degree of this polynomial? If I were to multiply this thing out, wouldn't I get, if I multiply the whole thing out, I'm going to get, when I FOIL that out, I'm going to get an x squared as my leading term. But when I distribute the 4, I'd get a 4x squared plus some other junk. When I distribute that 4x squared to the leading term of this factor, I would get an 8x cubed plus some other junk, right? Everybody agree? Okay, if I were to do all that stuff, I'd have to do a little bit of work to figure out what the other terms are, but the leading terms are easy to find, right? Those are just what I get when I distribute leading term to leading term. Okay, so what's the degree of this polynomial then? 3. Everybody agree? It's 3. So how many zeros does it have? How many complex zeros does it have? For sure. 3. Yeah, it does. It has 3 complex zeros, guaranteed. Has 3, and these zeros might be complex. Okay, and we should say that has exactly n complex zeros. Okay, meaning they could have imaginary parts. All right, well, we found all the zeros, and the zeros are 2 and 3 halves. How do we account for the fact that there are 3 if I only see 2 numbers up there? Anybody know? I'll give you a hint. One of those zeros counts as 2. Which one? Yeah, the 2 does. How come? Because it's squared. If I wrote that out, wouldn't that really look like, if I didn't square that, if I wrote them as separate factors, it would be 4 times x minus 2 times x minus 2 times 2x minus 3 equals 0. And so I would have gotten the factor x equals 2 twice. Agreed? So there really are, it's what we call a double root or a double zero. Okay. Notice that in the fundamental theorem up here, it tells us that, yes, this is true, including multiplicities. Well, because this factor is squared, it's telling us that this 0 right here has a multiplicity of 2. So it counts as 2. And then if we count up the zeros, we get 1, 2, 3, we got it, right? Drop the pen. Okay, agreed? Okay. All right, to kind of explore new stuff, I want to put it in the context of some old stuff, to sort of warm up to this a little bit. So let's look at this first problem that we could have done easily last unit. You still could do it, of course. So if I want to solve this, wouldn't I just put it in standard form first, push all the terms to one side and set it equal to 0? Then we look for magic numbers, and they exist. Numbers that multiply to negative 14 and add to negative 5 are just negative 7 and right? Those are my magic numbers, negative 7 and positive 2. And if I find the zeros, then I get the zeros, either x equals 7 or x equals negative 2, okay? And we can see if we look at a graph of this thing that sure enough, those correspond to the x-intercepts of this function, okay? No big surprise, okay? It's a quadratic function, there's our parabola. How about this one? How could I solve this equation? And think about the easiest possible way. I mean, I could factor it as a difference of squares, right? I could. But is there an easier way to solve that one? Say it again. Liliana, did you have an idea? Oh, right here, Adelaide? Okay, move the 4 over and isolate the x, right? Remember we said something last unit. We said that for quadratic functions, this is unique to quadratic functions, if I can point to a single variable, I can isolate it. It works for linear functions or quadratic functions. So we could do that here, right? I could add the 4 to the other side and get x squared equals 4. I could square root both sides and get, x equals what? Plus or minus 2, right? I get 2 real zeros. And that's what we see when we graph it. Okay, I got 2 x-intercepts. How about this guy? Now, I can't use, there is no sum of squares pattern, agreed? So I can't even use a factoring pattern, but I could solve here. I could do the same thing, right? I could say I could subtract the 4. Oh, darn it, what did I just do? Oh. There we go. Okay, so now I could subtract the 4 and get x squared equals negative 4, square root both sides, and get x equals plus or minus what? Yeah, what is the square root of negative 4? 2i, there you go. When I have a negative inside the radical, it turns into an I, doesn't it? So I get plus or minus 2i. Are those real zeros? So are they going to show up as x-intercepts? No, they're not, are they? And they don't, right? That one does not cut through the x-axis. Okay, agreed? Okay. What about this guy? Okay, let's do this one. So same kind of thing. I could push the 4 over to the other side and get x squared minus 2x plus 5 equals 0. Put it in standard form. Does that factor? Do magic numbers exist that multiply to 5 and add to negative 2? No. So we got to use something else. We could complete the square, or we could use quadratic formula. Well, we're always using quadratic formula. Let's do one completing the square. How about? So we want to complete the square, and this is a good candidate for that. It's easy to do if we choose to, because A is equal to 1 and B is even. So completing the square is a piece of cake on these, right? This is actually, it's pretty easy to do. This is how I would do it. I wouldn't even use quadratic formula. So we've got x squared minus 2x, leave a space, chase the 5 over to the other side, right? Okay, so then what's the number that I would have to add to both sides to create a perfect square trinomial here? Remember how we did that? Completing the square. It's been a while. Didn't we do half of b squared? Okay. So it'd be 1, wouldn't it? It'd be negative 1 squared, which is 1, right? And so that's going to factor into what then on this side? It's a perfect square trinomial. My magic numbers are what? Well, negative 1 and negative 1, right? So I get x minus 1 squared equals negative 4, right? Now what? Square root. Okay, good. So I get x minus 1 equals plus or minus, and we already did that, didn't we? That's plus or minus 2i. And then the last thing left to do is just to add the 1 in front of the plus or minus, right? And we get, and I told you to do that for a reason. You'll see here in a second. So we get x equals 1 plus or minus 2i. Now, how would you describe those two answers? I get 2 zeros there. I get 1 plus 2i and 1 minus 2i. If I have the same two terms, but I'm separating the two terms with opposite operations, one's plus and one's minus, what do we call those? Conjugates. And because they have i's in them, they're complex conjugates, right? Okay. Well, this is not an accident. This is not an accident. This is a really important relationship. This is called the complex conjugate root theorem. It tells us that if we've got a regular polynomial with real number coefficients, the only kind we're going to work with until eventually you might take a complex analysis class in college where you might look at some other weird polynomials that have imaginary coefficients, okay? But that's years away. We're looking at regular polynomials with real coefficients. If a plus bi is a complex root or a complex zero, then guaranteed its conjugate is also a complex root every time. So in other words, another way to say this that I think is even better is to say that complex roots with imaginary parts always come in complex conjugate pairs. Every time. They always come in complex conjugate pairs. So then if complex zeros or complex roots always come in pairs, that gives us a little insight into the possible kinds of solutions we can get to any polynomial. So if we have a 5th degree polynomial, how many complex zeros is that guaranteed to have? Absolutely guaranteed. It's going to have 5. Guaranteed. It has to have 5. Okay, so how could those, what could those be? Well, they could all be real. I could have 5 real zeros and no complex zeros, in which case I'd have 5 x-intercepts maybe, right? Okay, or I could have some double zeros, and we'll talk about that in a second. What else could we get? Could be 5 reals and no complex. Could I get 4 reals and 1 complex? That sound reasonable? Okay, but remember, complex zeros always come in pairs. I can never have a singleton imaginary zero. So that's impossible. So what's another one I could have? 3 and 2 would work, right? 3 and 2 would work. I could have 3 reals and 1 pair of complex conjugate solutions, right? What's the other one I could have? 1 and 4. There's only 3 possible things that could happen, and those are the 3. Okay? Make sense? Okay. All right. So what about this guy then? Let's talk about this. So if I solve this thing, I'm just going to push the 2 to this side. X squared minus 2x plus 1 equals 0. Well, how's that factor? What are my magic numbers there? -1 and, say it again, -1 and -1, right? So that's a perfect square trinomial. So this factors into x minus 1 squared, right? Everybody agree? Okay. Well, then my only 0 is x equals 1. Okay, well, we already know how we can square this. This thing has to have 2 complex zeros. What's the multiplicity of 1 here? It's 2, so it counts as 2, doesn't it? So therefore, it's only going to show up on my graph as a single x-intercept, right? There's only one x-intercept here, but it counts as 2. So now here's my next challenge to you. Can you see a pattern? Can you sort of infer how you could tell from the graph if a real 0 had a multiplicity higher than 1? Okay, let's look back at some of these previous graphs. Okay, this one had no x-intercepts, right? Had no real zeros. Now here's an example of one that it was a second degree polynomial that had 2 real zeros. Both of those real zeros had multiplicities of 1, right? They were single factors. Here's another one. It had 2 real zeros with multiplicities of 1. The powers of those factors were 1. How do those x-intercepts here and here look different than a real 0 with a multiplicity of 2? What's the difference? True, but looking at that graph, how is this x-intercept different than those x-intercepts? You see a difference? There is a difference there. There's a difference. Look at these. These x-intercepts or those x-intercepts. Look what's happening to the function when it encounters the x-axis. It's cutting straight through the x-axis, right? Everybody agree? That's not happening there. It's bouncing, right? It's a vertex. See the difference? So when you see an x-intercept that bounces, it doesn't cross the x-axis. If it bounces and it looks like a parabola, then well, that's a multiplicity of 2, right? Because it has the shape, that x-intercept has the shape of a second degree polynomial, right? It looks like a parabolic bounce. That's pretty cool, isn't it? This stuff to me is just fascinating that it all works out this way. Okay, we'll come back to that. We're not going to do a lot with that right now, but we'll come back to that at the end of the unit. Okay, what about this one? So here, how much time we got? I hope we have time for maybe just one more. That I'd really like to. Do you guys know what our schedule is? I don't have it memorized. How much time we have? Okay, so we might be able to do one more. So what about this guy? If we go back and we apply the same reasoning we did when we solved for x when it was an x squared function, we can point to a single x so we can isolate it, right? Sounds good. Okay, well, what happens here? If I isolate this thing, I get x cubed equals 8. Well, I could just take a cube root of both sides, right? What's the cube root of 8? 2. We got it. We got it, right? We got it. And I bet you $1 to donuts here that this, don't want to do that. I'll bet you $1 that we're going to get 1x intercept at 2. And we do. What do you know? Okay? Okay, what's wrong with that, though? There's a y-intercept. And we could find the y-intercept by just setting x equal to 0. But did we get all of the zeros? We found 1 0, didn't we? Does that 1 0 have a multiplicity of something greater than 1? It doesn't. It doesn't. Look, it just cuts right through the x-axis, doesn't it? Okay. Where'd the other two go? We lost them, didn't we? We didn't find them. So there's a very important moral to the story here. If you want to find all of the complex zeros, if you have a polynomial higher than degree 2, bigger than quadratic, you cannot simply isolate x. You can't do it. If we isolate x for a cubic like this, something that's bigger than second degree, we only got the real zeros. We want to get all of them. We want the complex zeros that have imaginary parts too, right? So we've got to do something different. Well, here's what we do. Everyone sees the dilemma here, right? We didn't get them all. We only got one of the three, okay? There must be a complex conjugate pair of zeros that we lost somehow. Okay, here's how we do it. We've got to introduce some new patterns. So we already know that the sum of squares has no pattern and the difference of squares has this pattern, right? Has this conjugate pattern. There's two other patterns though, the sum and difference of cubes that we also need to learn. Okay, so how do these go? If I have a difference of cubes, I'm going to teach you a way to memorize this, and this is probably where we'll end up for today. Sum or difference of cubes, you know that you're going to get a linear factor and a quadratic factor. The linear factor just has the terms a and b. The quadratic factor has the three terms a squared, a times b, and b squared. Okay? How do the signs go? There's a little way you can remember this. If it's a difference of cubes, then you know that the linear factor is a difference. So it inherits whatever kind of a pattern this is. The linear factor inherits that operation. It becomes a minus, right? And then look what happens. It just flips on the second one, and the last one is always positive. So a difference of cubes would factor into the quantity a minus b times the quantity a squared plus ab plus b squared. Same rule applies to a sum of cubes. It's going to factor into the quantity a plus b, then it flips to a squared minus ab, and it's always plus b squared. Everybody see that? Okay, so we could use that pattern now to go back and redo this problem. I could see this as a difference of cubes, right? This looks like x cubed minus 2 cubed. So that's going to fit our difference of cubes pattern. It's going to factor into x minus 2, right, times x squared plus x times 2, which we'll call 2x, plus 2 squared, which is 4. And all of that is equal to 0. You see where we're going to get our other factors then? When we apply the zero product property, look what happens. We get x equals 2. There's our real 0. And the quadratic factor in these difference of cubes or sum of cubes patterns always ends up being an irreducible quadratic, meaning it's always going to give us imaginary zeros every time. Okay? So if I apply the quadratic formula here, look what happens. I get x equals negative b plus or minus the square root of b squared minus 4 times 1 times 4 all over 2 times 1, right? Okay, so that's going to give us x equals negative 2 plus or minus the square root of 4 minus 16 is negative 12, all divided by 2. So let's split that up. That's going to give me negative 2 over 2 plus or minus. Square root of 12 is 2 radical 3, right? Times I, because I've got a negative, over 2. Well, the 2's cancel, the 2's cancel. And look at this. I got x equals negative 1 plus or minus the square root of 3i. There's my other 2. Cool, huh? Okay, we'll pick this up next time. Good job.